on the definitions of open and closed sets in metric spaces that we have already done, and introduce new concepts called the closure. We'll talk about boundary points and limit points of sets, okay, and how all of these are really connected to one another. So a very quick recall, given a metric space SD, S is my space, D is my metric, and suppose you have a set E which is contained in S, then we defined the closure of E as E naught. So this is, sorry, not the closure, the interior of E as E naught, right? This is the set of all interior points of E. All those points in E which have the property that there exists a ball centered at that point, which is contained completely within E, right? So that's E naught, the interior of E. Next, we said that E is open if E is the same as its interior. In other words, a set is open if every point of the set is also an interior point, right? And then finally we said that E is closed if E complement is open, right? So this is how we defined open and closed sets in metric spaces. So now we are going to build on these new concepts using these ideas that have already been developed, right? The first thing we are going to define is the closure of the set E. The closure of E, which we denote by E bar, okay, is defined as follows. It is the intersection of all closed sets containing E. Okay, so how do you define the closure? You look at the collection of all closed sets of which E is a subset and take the intersection of that collection of closed sets. That intersection is what we denote by the, that is what we call the closure. Okay, so there are a few immediate observations that we make. Firstly, the closure is by definition the intersection of a bunch of sets that contain E, right? So therefore E is contained in every element that goes into the intersection. In other words, E must be contained in its closure, right? So E, for any set E, E is contained in its closure. That's the first observation. Secondly, we note that the closure is by definition an intersection of a bunch of closed sets, and we have already said that intersection of closed sets is a closed set, right? Additionally, we know that for any set E, the closure is in fact closed. Okay, so these are two immediate observations. And now if you stare at the definition a bit more, you should also get more of an interpretation of what is the closure, right? It's the intersection of all closed sets containing E, and it's also closed. So effectively the closure is the smallest closed set containing E. Closure is the smallest closed set containing E. Okay, so this is how you define the closure of a set. Let me go through a couple of examples. It may not be immediately clear why these statements are true, but they will get justified over the course of this video, right? So the first set I want to consider is the semi-open, semi-closed set 0, 1, where 1 is included and 0 is excluded. Okay, so it turns out that the closure of this set is in fact the closed interval from 0 to 1, right? And again, a formal justification of this will in fact come shortly. Okay, so for now just believe me that this is in fact the case. Okay, similarly, let me talk about the closure of an open ball. So suppose I'm looking at X in Rk such that the distance between x and x naught is less than r. Okay, so this is the open ball of radius r centered at x naught. The closure of this set is in fact the closed ball of radius r centered at x naught. Okay, so these are just a couple of examples of closure. At this point, it may not be immediately obvious how to apply the definition, because it looks like, how do I even think about all of the closed sets that contain a particular set, and how do I think of its intersection and so on. These things may not be obvious now, but we will see that there are other equivalent ways of thinking about closure as well. Okay, so that's the first concept I wanted to introduce, namely the closure of a set. Okay, the next thing is we are going to talk about boundary of a set, or equivalently boundary points of a set. The boundary of a set E is defined as the closure minus the interior. Okay, so the boundary of any set E is defined as essentially the set consisting of all of those points which lie in the closure but not in the interior. So in case the set minus notation is new to you, let me just quickly introduce it. A minus B is essentially A intersection B complement. So again, the elements that are in A but not in B. So if you want your Venn diagram representation, if this is the set A and if this is the set B, this bit is A minus B. Okay, so once again, the boundary of a set is basically the closure of the set minus the interior of the set. Elements that are in the closure but not in the interior. Okay, those points are called boundary. The collection of those points is called the boundary, and the set of all points on the the points on the boundary are also called boundary points. Okay. So once again, let's do a couple of examples. Let's in fact keep the same examples that we did before. So it turns out that E, suppose you take E to be the set 0, 1. Now, if you believe me for now that the closure of the set is the closed interval from 0 to 1, then it's easy to see what the boundary is, because the closure is the closed interval 0, 1. Stare at this set and convince yourself that in fact the interior of this set is the open interval 0, 1. In other words, the boundary points are essentially 0 and 1. Right, that intuitively lines up with our notion of a boundary, because these are in fact the points that are quote unquote on the boundary of the set, right? Yeah, so there are two boundary points. Another thing to note here is that one of the boundary points in this case belongs to the set E, namely 1, and one of the boundary points does not belong to the set, right? So boundary points don't necessarily, the boundary can consist of points that are within the set E and can contain points which are not within the set E. Okay, another example. Let's take E to be once again the open ball of radius r centered at x naught. Now this is in itself an open set, so it is its own interior, and the boundary is the closure is in fact the closed set, where the distance from x naught is less than equal to r. So therefore, by definition, the boundary in this case would be those points which are exactly a distance of r from x naught. So this implies that the boundary points are all x such that d of x comma x naught is equal to R. Right? Which kind of also should make some intuitive sense. You have an open ball, and the boundary is basically all the points on the surface of the ball, so to speak. Right? Those are your boundary points. Okay, so that's the second of the three concepts that we had to introduce. The next thing we will talk about are limit points. Okay, so by definition, a point, let's say x, is a limit point of E if there exists a sequence xn which lies completely in E. So xn belongs to E for all n, and xn is in fact converging to x. Right? So this definition also kind of makes sense. A point is a limit point of a set E if you can construct a sequence in E which converges to x. Okay. As a temporary notation, let me denote the set of limit points by elim. Okay, this is not standard notation. E naught and E bar are standard. Elim is not standard. I'm only introducing it temporarily, and we will see soon that elim can in fact be expressed easily in terms of the notation already developed. So it's essentially temporary notation for now. Okay, so it's a set of all limit points. Now, one thing I want to point out is that the set E is always contained within elim. In other words, every element of E is necessarily a limit point. Why? Because I can construct a constant sequence taking that value, which of course trivially converges to that point. Right? So every point in a set is also a limit point, but you can also have limit points which do not belong to the set E. Okay, let us see again with our running examples. Let us see what happens. So suppose I take E to be the semi-closed semi-open interval 0 1. Now in this case you should be able to in fact convince yourself that so all the elements of E are of course also limit points, but in addition the element 0 is also a limit point of the set, because I can construct a sequence within E which in fact converges to 0. So in this particular case you will see that the set of limit points is in fact the closed interval 0 1. Right? Again, the other example is, suppose you take E to be the open ball of radius r centered at x in Rk. Centered at x naught. In this case, again, probably takes a little bit of thought, but in fact, the set of all limit points of the set is in fact going to be the closed ball. Right? So these are a couple of examples of limit points of sets. You will observe from both these examples that in fact the set of limit points seems to coincide with the closure of the set, and that is in fact not a coincidence. So as we will prove shortly, limit points are in fact precisely what constitutes the closure. Okay, fine. So now that we have introduced the three concepts that we wanted to, now we will write one lemma which in some sense summarizes all of these results. So I'm going to move on to the next page for this. Lemma. So let E be a sum set then the following are true. The first statement of the lemma is that E is closed if and only if E is equal to E bar. Right? In other words, a set is closed if and only if the set coincides with its closure. So it's worth contrasting this definition to the definition of an open set. A set is open if it coincides with its interior. A set is closed if it coincides with its closure. Okay, so that's the first of our statements. The second is that an element is in the closure of E if and only if it is a limit point of E. Right, so something belongs to the closure of E if and only if it is a limit point of E. So this essentially tells you the claim that I've made in words earlier, namely that the closure of a set is in fact identical to the set of its limit points. Okay. Again, this is also something worth pondering over. What it tells you is that there are two equivalent ways of thinking about closure. A so-called outward definition and a so-called inward definition. What would the outward definition of a closure of a set be? You look at all of those closed sets that contain E, okay, and then take the intersection of all of those closed sets to find the quote-unquote smallest closed set that contains E. Well, that is the closure. Another way of thinking about closure, equivalent way of thinking about closure based on this statement, is a so-called internal way of thinking about closure. Closure is basically all of those points which can be obtained as limits of sequences in E. Right? So all the points that you can approach via sequences in E. Right? And these two are in fact identical. Okay, that's what this statement says. We will prove it shortly. Statement 3 is in fact a consequence of statements 1 and 2, which says that E is closed if and only if E contains all its limit points. Right? So in other words, what the statement says is that E is closed if and only if A is equal to E lim. Right? So again, pause if you want and stare at this and convince yourself that statement 3 is in fact a trivial consequence of statements 1 and 2. Because for any set, we have said that the closure and the set of limit points coincide. So given that closed sets are those that coincide with their closure, it also follows that closed sets are those that coincide with their set of limit points. Okay, that gives you another way of thinking about closed sets, if you will. And the last statement of this lemma is actually regarding boundary points. A point is in the boundary of E if and only if it lies in the closure of both E and E complement. Right? Again, this kind of gives you some an intuitive interpretation of what it means for a point to be on the boundary. See, because the only way you could possibly be in the closure of both E and E complement is if you lie on the boundary of both E and E complement. So another way of interpreting statement 4 of this result is that points on the boundary of E are the points that lie on the both on the boundary of E as well as the boundary of E complement, right? And hopefully that makes intuitive, that's intuitively consistent with your own idea of what boundary means, right? From an English standpoint. Okay, so now these are your 4 statements of the lemma. What we are now going to do in the remainder of this video is go through a proof of these very quickly. Okay, now statement 1 is in fact trivial. There's not much to be done. If E is equal to E bar, then clearly E is closed since E bar is closed. Right, so that's one side of the lemma, that if E is equal to E bar, then E must be closed. If E is closed, then it is in fact clearly the smallest closed set that contains E, right? Then the intersection of closed sets containing E must clearly be E. In other words, E bar is equal to E, right? Also straightforward. So the proof of the first statement is actually fairly straightforward. Now let's focus on the proof of the second statement of the lemma. Second statement of the lemma is that an element lies in E, the closure, if and only if it is a limit point. In other words, if X belongs to the closure, it must be a limit point, and if X is a limit point, it must belong to the closure. So there are two parts to this equivalence, of course. So suppose that X belongs to the closure, right? We want to show that X is therefore also a limit point. We will prove this via contradiction. So suppose X is in fact not a limit point. Okay, now what does it mean to say that you are not a limit point of E? In other words, it is not possible for you to construct a sequence of elements in E which converges to X, right? In other words, it is not possible to find elements of E which are arbitrarily close to X. So a consequence of this supposition that X does not belong to the limit set of E is that there exists some positive radius R such that if you look at the open ball of radius r centered at x, let's say y, such that the distance between y and x is less than r, this set has no intersection with E. Yeah, so the fact that X, or the statement that X does not belong to elim, implies that there is some ball centered around X which has no intersection with E. In other words, there are no points in E which are any closer than R to X. Okay, what is the consequence of this? Well, since this A is an open set, since A has nothing in common with E, A complement contains E, right? So A complement is a closed set and it contains E, right? And since the closure is the intersection of all closed sets that contains E, it follows that E bar must be a subset of A complement. Now A contains X, so A complement does not possibly contain X, and so it follows that X could not possibly lie in E bar, right? And that's your contradiction. Okay, so we started off by assuming that X belongs to the closure. We supposed that X is not a limit point, and from there showed that that would imply that X does not belong to the closure of E, and that gives us a contradiction, right? So this is how we know that any element that belongs to the closure must necessarily also be a limit point, right? So this is part 1 of the statement. Now we have part 2. So suppose that X belongs to the limit set. How do I know therefore that X how do I know therefore that X must also lie in the closure of E. So suppose X does not belong to the closure of E. Okay, again, for the purpose of getting a contradiction eventually. What does it mean to say that X does not belong to the closure? It means that X actually belongs to the complement of the closure. Okay, and this, remember, is an open set. So the fact that X belongs to an open set, which is the complement of the closure, implies that there must be again some ball of radius R such that the set Y such that distance between Y and X is less than R has no intersection with E complement, sorry, E closure, which in turn implies has no intersection with E. Right? So make sure that this is comfortable with you. What we are saying is that suppose that X is in fact not in the closure of E. The fact that it's not in the closure of E implies that it must belong to the complement of the closure. The closure being a closed set means that its complement is an open set. What does it mean to say that you belong to an open set? That means you are in fact interior to that set. So which means there must exist an R such that the open ball of radius R centered at X, which is what this is completely contained within E bar complement. The fact that it's contained within E bar complement implies that it couldn't possibly have an intersection with E. That's what has been written now. And now if you stare at this, you can see that this contradicts the fact that X is a limit point, right? Because if you're a limit point, I can construct a sequence in E which converges to X, but you couldn't possibly if there is a ball around X that has no intersection with E. So this contradicts the statement that X belongs to elim, right? And that completes the argument. So we have showed in two parts that if X belongs to the closure of E, it must also be a limit point. If X is a limit point, it must also lie in the closure. So putting all of that together, we have basically proved that the closure of a set is in fact identical to the set of limit points of the set, right? Which is also what makes this elim notation that we have temporarily set up ultimately redundant. Okay, so part 3 I'm not going to do because it's a trivial consequence of 1 and 2. So I leave it to you to convince yourself that statement 3 of the lemma holds. Let me move on to statement 4. Okay, so let me remind you once again what statement 4 is. A point lies in the boundary of E if and only if it is in the closure of E and E complement. Okay, so now let's go about proving this. Now, based on the previous parts, we know that points in the closure of E and E, to say that some point is in the closure of E and E complement is equivalent to saying that that point is a limit point of both E and E complement. Okay, so one side of this is actually quite easy. So this part is easy. Why? Because the fact that you are a limit point of both E and E complement implies that the point, so suppose that X lies is a limit point of both E and E complement, it could not possibly be an interior point of E. The fact that it's not an interior point of E implies that, well, it must lie on the boundary, right? So that part of the implication I'm going to leave to you to fill the details of. Let me instead focus on this, which is the perhaps the less trivial of the two sides. That is, suppose that a point lies on the boundary of E. So suppose X is on the boundary of E. that is belongs to the closure of E minus the interior of E. How do I now argue that it must lie in the closure of E and E complement? So as I said before, it suffices to show that X is a limit point of E and E complement. In other words, no matter how small a ball you draw around X, it contains both elements of E and E complement, right? Which is what allows you to construct a sequence lying in E that converges to X, and also another sequence lying in E complement that converges to X. Okay, so so the way one would argue this is simply the following. So for any R greater than 0, an open ball, let's call that open ball. I don't want to write the full notation again. Let me just call that ball as X comma R. The open ball of radius R centered at X, that's the notation here, satisfies the following property. It contains elements from E. Okay, why does it contain elements from E? Because it lies on the boundary of E, and so therefore it is a limit point of E, right? Since X is, right, remember X belongs to the boundary of E, so therefore it belongs to the closure, and so it is a limit point, right? Since X is a limit point of E. Similarly, the set BXR, the open ball of radius R centered at X, also contains elements from E complement. Okay, and why is that? Well, because X is not an interior point of E. Right? Because if X, so convince yourself of the second statement, if X were interior to E, there would exist an R such that an open ball of radius R is contained completely within E. The fact that it's not an interior point implies that no matter what open ball of radius R you choose, there will in fact be some elements not in E that is contained in that set, right? So putting this together, you see that no matter what radius R you choose, an open ball of radius R centered at X contains elements both from E as well as E complement. This in turn allows you to construct a sequence entirely in E which converges to X, and a sequence entirely in E complement that converges to X. So therefore X is a limit point of E as well as E complement. Right? That completes the argument. Right? So in a sense we have proved that lemma. I hope this basically, so this is something that particularly if you're seeing this for the first time, you should go back and stare at every statement of that lemma and try and understand what the implication is. Put together, it basically relates all of the notions that we have introduced so far: the interior of a set, the closure of a set, what is an open set, what is a closed set, what are boundary points of the set, what are limit points of the set. So all of these concepts are in some sense related to one another via the lemma that we have just proved. Okay, so we'll stop here and continue our coverage of metric spaces in the next video.